Hello students, welcome back. We completed up to section 4. Now let's go to section 5, Riemann Integrability. Here's a definition of Riemann integral so far. The Riemann integral is defined as the limit of Riemann sums, all Riemann sums, where the subinterval size all go down to 0. You see this delta x is the maximal subinterval size. So maximum is going down to 0, so all rectangles are getting infinitesimally thin. But then again, how do we control this limit? It's not a limit of one function or one sequence. This Riemann sum, we are talking about really humongous quantity. Not humongously large, but humongously many. In fact, uncountably many. Let's go back to this partition idea. How many partitions can you think of? Well, there are uncountable many different choices even for a fixed n value. And n will become, of course, infinity. So we're talking about something uncountable, and then that getting larger, larger, larger. And that's not all of it. Look at Riemann's sum. This yi's are selected anything between the minimum and maximum. How many are there? Of course, there are uncountable many. And then that's for a fixed partition with n subintervals. And n value is getting larger and larger and larger. And for each n value, we have uncountably many. You know, we are talking about something really humongously humongous. It's really, really difficult to control this. How are we going to do that? Our idea is to use some kind of sandwich rule or some pinching, squeeze rule. We're going to overestimate as badly as possible and underestimate as badly as possible. You see, bad is good. Bad behavior, terrible approximation is better in this case. Why bad is good? Really badly behaving cases, the maximum and the minimum, and everything else will be captured in between. If the two worst cases, the maximum case and minimum case, the overestimation and underestimation, merge down together to the same limit, that means everything will be squeezed and then end up with the same limit. So that's what we're up to. We're going to do some terrible overestimation and terrible underestimation. And remember, being terrible is good. Bad is good. The worst, the better. That's our strategy. We're going to call those as the lower Riemann sum and the upper Riemann sums. The smallest possible versus the biggest possible. Would you like to see some illustrations? Okay, here are some illustrations of arbitrary Riemann sum. Okay, we have this continuity here as well, and then arbitrary Riemann sum. Run it again, we have something different. Still terrible. Still terrible. Again, remember, the more terrible, the better. Now, a lower Riemann sum. You see, all these rectangles touch the graph, but from below, because we're taking the minimums. So run it over and over again. No matter how many times I do, all those rectangles are touching the graph from below. Lower Riemann sum. So some of those rectangles here should be less than the actual signed area, if the actual signed area exists, of course. That's a problem. It may not always exist, but if it does, then there should be lower estimation. How about upper estimation or overestimation, which we call upper Riemann sum? Well, here we go. All these rectangles are touching the graph from above because I'm taking the maximums. You see? So the Riemann sum, the sum of all those rectangles, should be an overestimation. It should be bigger than the actual signed area if the signed area exists. How do we express those algebraically? Like this. For yi star value, we take the minimum or the maximum. And how do we express minimum? Lower bar is the minimum and upper bar is the maximum. That's widely accepted notation as a matter of fact. And we are going to use lower bar for lower Riemann sum and upper bar for upper Riemann sum. Okay, it's a bit cumbersome to write like this, minimum of function value f of x in this interval. So let's abbreviate it as yi lower bar for minimum, yi upper bar for maximum. And they correspond to these illustrations. You see lower bar for minimums, upper bars for the maximums. One more thing to remember, any yi value is between the minimum and the maximum, and getting all the minimums added up versus all the maximums added up certainly will be smaller and bigger comparatively speaking, so that's what you're going to get. All the Riemann sums will be captured in between the lower estimation, the lower Riemann sum, and the overestimation, upper Riemann sum. So this is an underestimation, and that's an overestimation, lower Riemann sum and upper Riemann sum. Okay, all right, back to our strategy. We're going to control this Riemann sum from above and from below, and we're going to squeeze everything. But how are we going to squeeze the lower and upper Riemann sums? Here comes the answer. Let's begin with this idea of refinement first. We say a partition Q is finer than partition P if all the points of P belongs to Q. As you can see from the first picture, partition P is blue and partition Q is red. There are 6 points in Q and 4 points in B. But not only that, all the points in P belongs to Q. And we have a couple of extras here. So Q is finer than P. Q is a refinement of P. Now if you look at the second picture, then R has 5 points and P has 4 points, but neither is finer than the other because P2 does not belong to R and R2 and R3 are missing. And of course I can make this R finer than P by including this P2 as well, and that'll become of course this Q. So if you have two partitions, then you can always take a refinement. Just include everything, take the union of all, then I'm going to get final partition. Now under the refinement, please make this observation. Lower sums must increase and the upper sums must decrease. Here's an illustration. Here's a lower Riemann sum. You see all the rectangles are touching the graph from below. And then here's a refinement, 3 more points, and consequently we have smaller subintervals, and in smaller subintervals the minimums increase. You see the minimum of the entire interval, that's the smallest possible, so down here, and minimums for these smalls will go up as much as touching those graphs. Same goes here. So the conclusion, lower sums increase as we get finer, finer, and finer. Same goes to the upper Riemann sums. Upper Riemann sums decrease as we go finer, finer, finer. You see, the big interval here, the maximum there, but you're taking subintervals, so some maximums of those subintervals are smaller. So lower sums increase and upper sums decrease. And yeah, P becomes Q as get finer, P becomes Q. lower sums increase, upper sums decrease, and of course upper Riemann sums are all overestimation, so they're always bigger than all the lower estimations, vice versa. And then the real signed area must be captured in between, if it exists. If it doesn't exist, then, well, still overestimation. Upper Riemann sums are going to be bigger than lower Riemann sums, yes, but there will be a gap. In any case, we have a tool. We're taking refinement. If you have two unrelated partitions, then we just include them all, take the union of everything, and make a refinement, and make it finer, finer, finer. And if you do that, naturally the subinterval width will become smaller, smaller, smaller. And by repeating this, lower Riemann sums increase and upper Riemann sums decrease. If you take the limit of all those, limit of lower Riemann sums is an increasing limit, and then limit of upper Riemann sum will be decreasing limit. And then of course upper Riemann sums are always bigger than lower Riemann sums, so if you apply the limit rule, limit of bigger function must be limit of a smaller function. Bigger remains bigger, smaller remains smaller. Remember all those? I should have said bigger than or equal, or smaller than or equal, of course. If you have strict bigger, well, the limit rule makes it bigger than or equal to. Now, do we actually have equality here is a question. So here's a summary. Lower Riemann sums increase as you go finer, 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 and that increasing limit is called the lower Riemann integral. Upper Riemann sums get smaller, smaller, smaller as you get finer, 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 and that decreasing limit is called upper Riemann integral. And lower sum is of course less than upper sums, so the limit rule stays. Upper Riemann integral should be greater than lower Riemann integral. So increase this way, decrease this way, and then limit of higher quantity is bigger than limit of a lower quantity, yes. Now the question, when do they become the same? If there's a gap, then we won't have well-defined signed area. If they're the same, that's the quantity we are looking for. So there. Low Riemann sums increase, upper Riemann sums decrease, so that we have low Riemann integral less than or equal to upper Riemann integral. And if they're the same, that's a big if, but if they're the same, then we're going to call this common quantity as Riemann integral. If this happens, then let's go back to that. By squeeze rule, every limit of all Riemann sums will converge to this common quantity, because all those has to be greater than or equal to this and less than or equal to that, and these two are the same. So they all merge to the same value, which we call the Riemann integral. So that's how we can define Riemann integrability, using the concept of overestimation, upper Riemann sum, and the underestimation, lower Riemann sum, and their limits, upper Riemann integral and lower Riemann integral. When they become the same quantity, the common quantity, is called the Riemann integral. And if this happens, then all Riemann sums converge to the same common quantity because of this squeeze law. Now, what is the practical condition? When do we have Riemann integrability? That's going to be a topic of the next video when we are going to talk about the fundamental theorem of calculus. Basically, if you have a continuous function, then it's Riemann integrable, yes. But there are discontinuous functions that are Riemann integrable too, so that's a bit different story. But in any case, if continuous, then everything works okay. Let's come back and discuss that. Stay tuned.